Anyway, so my name is Sami Laiho. I'm a Chief Research Officer for TrueSec. So for those of you who have met me before, that might have been with my previous role. I was 12 years self-employed and had worked for my own company. But now I'm taken the global role of Chief Research Officer, and trying to take care of the technical sides of our TrueSec company and help our SOC and IR services to figure out new concepts on how to keep things secure. Just finished today with a 4-day training of troubleshooting and Windows internals. So I still do the same thing as I did before, and I'm going anywhere. I'm really, this is what I love doing. So I'm gonna keep doing this as well. I'm a Microsoft MVP in the core operating system. I've been one for about 12 years. Been in IT for 25. I've been doing this CQURE's advanced Windows security course for, I think, 3 or 4 years already. So happy to be back. Guess that means feedback was good from previous students. So I'm more than happy to be invited again. Today, what we'll go through is we'll go through if you would ask me, the most important topic of all Windows internals, which is the memory management. Everything in your computer happens in RAM. Nothing happens outside of it. You could think of the CPU as the brain of a PC, but on the other hand, the content of the brain is in RAM, except those small, very tiny registers that the CPU has tied to itself. But really, there are very few components in a PC that you have to have so that it will run, but one of them, of course, being memory. And memory management will play a huge role in everything, which means that it's one of the core skills of knowing your Windows internals. I always say that the most important rule in Windows troubleshooting is that you cannot know what's wrong unless you know what's right. So you should really dig into your Windows internals, and it got me into security. I started in security because it's super easy for me to find vulnerabilities and weaknesses because I know the OS so well. So now I know where to look for. I also know how to secure it very well because I've read all the manuals, and I really believe in core concepts of security. My specialty for the last 23 years has been getting rid of admin rights. I just a few months ago even had to tweet out that admin rights are not human rights because people seem to treat them like such. But core concepts are the thing in security for me, but my background is very strong in the operating system itself, and I'm more than happy to be teaching this from time to time as well. Operating system wise, I only have this slide here because I have been a trainer for 23 years, actually more than half of my life. So I would always start every training by talking about the licensing and versions of Windows, saying that Windows version, server version, this and this, enterprise supports this and this amount of memory. Actually, Microsoft doesn't really restrict the amount of memory anymore. So the real restrictions are based on the amount of virtual memory that's available. And if we're talking about RAM, if we're thinking about yesterday with Microsoft's M364 service being down most of the day, it's hard to believe that Microsoft actually doesn't support something unless they tested it. And when it comes to memory, physical memory limitations are really not limitations, but support is limited to something that they've tested it on. So currently the support for Server 2022 and SQL is 48 terabytes of RAM, but that's only based on the fact that that's the biggest machine that they've been able to test it. So it's actually not a limitation technically, it's just a limitation because they haven't tested it with anything else. But I'm not going to talk about things like that. Those are not core concepts. What we are going to delve into is how Windows actually deals with memory. And the first thing and the most important thing that we have to talk about is the concept of virtual memory and the memory manager. So the operating system itself does not show physical memory to any of the applications that are running. If your application would be running without virtual memory, then what the developer would have to do for the first thing when they started the application was that the application would have to go through physical RAM and see if there would be any empty pages anywhere. And if there were empty pages somewhere, then they could put something in it. Instead of that, every application starts its life by seeing a world that starts with an address 0 and ends with an address and that takes the burden of thinking about physical memory. It gives us a lot of other benefits as well. I'm getting paid for speaking. I'm not getting paid for drawing. So maybe one day you can get these originals and I can sign them for you because this art must be priceless at some point. But I am still going to bug you with my drawings, okay? And first of all, if we think about your application, if you have an application here, let's just change the color here. So we got an app here. I got another app here. That's another app. Now you have some hardware, physical RAM here. Now, when you have a memory page that the application needs, the application sees virtual memory. Okay, so there's VM, and this one sees its own virtual memory. Now, when this application starts writing to the first page, so this app starts to write to the memory and it starts writing this first page here, it believes that that's starting from an address of 0, but then it's the memory manager here in between. And memory manager will map that memory somewhere in the physical memory, and it will keep that information in what it calls page tables. And then this application here, it will start off with the same way. It starts by believing it's writing at the address of 0, and then memory manager takes care of mapping it into a physical memory. So you don't have to worry about the physical memory layout. Now, the good thing of this is, of course, as well, if we think about this app being Notepad, and then we get another Notepad. So you want to open another instance of Notepad here. It has its own virtual memory. Now it needs that binary where it starts from, and it starts from address 0 again, but this is the same page, which means that we can map it into the same physical memory page. So you're also conserving huge amounts of memory when you don't have to have that same content in RAM many times. So it has a lot of benefits. You can't live without virtual memory. The funny thing about Windows, even today, like even Windows 11, let me just open up this, and you can see that if I look at the performance settings here, this is just so stupid from Microsoft, but this says virtual memory. It says that virtual memory, but page file has nothing to do with virtual memory. Page file is not virtual memory. If you remove the page file completely, you still have virtual memory. So this is just wrong. But anyway, so page file is not extra memory. We'll get back to that, but that's something that you have to get out of your head after today. If you still think that virtual memory, if you still think that a page file is extra memory, it's not. Anyway, so that's kind of the basics. There's a lot of benefits to this, but if you think about how Windows operates, Windows needs anything that Windows can operate with needs to be in RAM. Windows can't use anything from the disk. If there's something on the disk, it needs to be put into memory, including the page file as well. I mean, if there's something on the disk, you cannot access it without it being in RAM. So RAM is like, it's almost like a buffer. It's one part of the memory chain. The fastest memory that you can ever have, that is the CPU and its own registers. We're talking about half the light speed of stuff. So that's super fast, super small. And then we go into layer 1, layer 2, maybe layer 3 cache of the CPU. Then we had the RAM, and then we have disk. There are a lot of people who want to turn on different kinds of optimizations when they have SSDs. So things like turning off superfetch when you have an SSD is really silly. Don't do that. There's no sense of doing that. So that's just because if we look at this memory chain here and people see a line like this, and this, if this would be 1 and this is RAM, then the other end of the spectrum is 100,000. That's your hard disk, but that's a spindle. It's 100,000 times slower than memory. Now, when people see that SSD is here, they start making assumptions like, I don't need to do optimizations because I have an SSD. I don't need to have superfetch. I don't have to use memory for caching. But they do not understand that for a SATA-based SSD, that's 50. With the modern NVMe disks, you can get up to only 10 times lower. But if we're talking about Optane memory from Intel, you could be only like a few times, 4 times slower than your RAM. I love cars. I used to go and buy cars based on how fast they were. Nowadays, I go to the shop and I buy a car that is the biggest one they have because I have a huge family. But if my neighbor's car is twice as fast as mine, I'm horrified. But 50? Come on, like that's like comparing a Ferrari to a bike. So honestly, why would you not use RAM? That's one of the biggest misconceptions of Windows, is that people think that you should have free memory. You're not supposed to have free memory. The more free memory you have, the worse you should feel, because that memory is supposed to be used. If you don't use the memory, it's unused resources, you're paying for nothing. So I don't understand where that comes from. That's a brain fart that people have, which is that I asked them, you have a CPU, it has a blazing fast cache, would you like to use it? Absolutely, of course, makes the CPU faster. All right. You have a hard disk, it has a very fast cache, would you like to use it? Oh, of course, that's a huge difference. Okay, great. You have a lot of memory, would you like to use it all? Absolutely not. I don't know where that comes from, but people have this insane thing of hogging memory. If you talk to Azure technicians and they see that they have 2 gigs of unused, let's say bigger scale, let's say 2 terabytes of unused memory in a server, they'll take it away. They'll physically remove it. So it feels weird removing. I mean, this would happen if I have a, let me show you. I got a demo environment here. This is my, I've been teaching kernel debugging today, so we have a few windows open here, don't mind those. If you look at this computer and we look at task manager, and I would show you that this is my memory currently. We have 87 gigs out of 512 gigs are used. And we're using 8 DIMMs, okay? What does that mean? That means that an Azure technician would take a calculator and say that 512 minus 88, it's 424, and we got 64 gig DIMMs. So remove 6 because you're not using the memory. That's taking energy. They have millions of servers. If they remove this unused memory, they save hundreds of thousands of euros every day for just electricity bills. You're supposed to use your memory, but we'll get back to that topic many, many times. RAM is kind of a buffer between the disk and the CPU there. It's part of the memory chain. Things from the disk have to go into RAM and then get processed somehow. Sometimes I make fun of my customers when they call me and they ask me, like, they call me and say, hi Sami, we have a performance issue, can you help us? Oh, yes, I can. It's your disks by. It's always the disks. When you look at memory, the memory has huge amounts of bits. I can't help myself. I made the mistake of opening up that chat, and now I can't help myself but to read. I think I'll read this, and then I'll think I might just shut it down and look at it at the end. Because John says that I think the desire for free memory comes from a day when the penalty of going to swap was so hard that people wanted to avoid it at all costs, not realizing the OS felt that way and would act accordingly. I think it's fascinating that Windows nowadays has a swap file again. Because many people think swapping is Unix and swapping is the old Windows 3 series and all the home versions of Windows. I think it's just fascinating that we are here to really talk about the page file. I mean, we're really here to talk about this. That's what we use daily now. But now this came back. It's your swap file. Swap file is used by the modern apps, those nowadays called universal apps. Those actually will change their whole memory content into a swap file in some cases, but that's more like the swapping that Unix does, as Windows is always page driven. But I can tell you now that you learned, because I always teach my customers some Finnish when I get the opportunity. A swap file, the Finnish word for a swap file is so much easier. It's called heittovaihtotiedosto. So now you know. And now I will hide the chat because I honestly just can't stop myself, because I'm used to students in class and interaction, believe it or not, but I'm used to interaction. So when we're starting to look at memory, we cannot address all the bits. I mean, you honestly can't do this. If you think about the memory, at the end of the day, the memory is just filled with bits. There's a lot of bits here. Some zeros, some ones, but a lot of bits. We can't address every bit. If we'd address every bit, we would have a huge page table. That's not efficient. So what we're going to do is we have a certain part of memory here that is the smallest particle that the memory manager understands, and that is a page. And this page is then translated into a virtual memory address. So page is the smallest component that the memory manager eats. So if you have the memory manager here, the memory manager is part of the Windows kernel. The memory manager will eat the page. That's the smallest one it knows, or it will want to know. If you're doing an application by yourself, then if you're coding an application, you might do a variable, which would be a Boolean value. So a Boolean variable would only be 1, 0, or 1. So that would mean that would be insane to take a huge page. These are usually 4K or 2 megs, so they're big. Now you don't want to sacrifice a 4 kilobyte page for storing a single 1 or 0 as a Boolean value. So when your processes consume private memory, they usually go so that this page eaten by the memory manager, this page is then actually fed. This page from here is fed to what's known as the heap manager. And the heap manager spills out small heaps, even down to like 8 bytes. So that will actually be the private memory that the processes use. So that's, you are not going to have a completely fragmented memory space because of these big page sizes. It's just that that's the smallest component for memory translation. There are some terms. I'm not going to read through all the slides. You can read the slides later on. You're only going to have me for a few hours, so I'm not going to read everything out loud. When we're talking about virtual memory, there's a lot of benefits for having it. So one was the developer's life. You can always start with 0. You don't have to worry about the physical layout. We can cheat the applications because we can run a lot more apps when we have virtual memory. Every application in Windows believes that it has different amounts of memory, and it doesn't have anything to do with physical memory. So if my computer has 32 gigs of RAM, like now, then applications see the same world as they would if I would have 512 megs of memory or 2 terabytes. There's no difference. Applications do not know anything about the physical memory. Benefit being that we can also page things out from memory into disk, into a page file or into a memory mapped file, even more often. So there is a big benefit in having the possibility of having a lot more applications running side by side. Applications take a lot of space, and when the applications start to load into memory, they need some memory to play with, and those memory locations, I mean that memory address that we have, that's what we know as a process. If you're still a person who thinks that Task Manager will show you what's running in your computer, please take my course. Task Manager will never, ever be able to show you what's running on your computer. Conceptually, that's impossible because Task Manager only shows processes, which are just a concept in memory. They can't even execute code. Windows is a multi-threaded operating system, which means that the threads run on a CPU, not the processes. So you actually can never, ever see anything with Task Manager when it comes to running code on your machine. Process is a memory concept. And when we launch a new application, we build a virtual world for every process, for every application. So the applications in user mode, they need to run in a process, and they're sandboxed against each other so that if Excel crashes, we don't have to crash Word because they live in their own virtual worlds. They have absolutely no idea of each other, which is great. Think about HoloLens. We can optimize because we only have to keep that part of information in memory that we currently need very fast. So if I would be wearing a HoloLens, which would be awesome, but if I would be wearing a HoloLens, everything inside of this room would have to be in my memory. It would have to be stored in the RAM of the HoloLens. Why? Because you really don't know how fast I'm going to turn my head. Okay. If we're talking about something that's behind the door there, we don't have to store it in RAM because it takes a little bit of time for me to get up and go and open the door. So there's enough memory. There's enough time to get that memory from the disk into RAM. But everything that's here visible very fast, it has to be in RAM. So we can also optimize. We don't have to use that memory. What if you need your own head? What if you need your own memory? I always say that the page file is kind of a book. It's your notebook. So if I have all phone numbers, this sounds idiotic to my kids because they don't understand who would ever know someone's phone number by heart. But I'm 43. I'm still one of those who still remembers phone numbers from my childhood. So if I have all the phone numbers in my head at the same time, at some point it's too much. What I can do is I can take a notebook and I'll write down the numbers. Okay. And I can put the notebook up there and I can use my resources for something else. If I want to know the phone number and you ask it from me and I'm going to spill it out of my mouth, I will have to, honestly, from this to your ears, It's not going to move from this to your ears. I will have to open the book and I will have to take it into my RAM, and then I can tell you what the phone numbers are. So it's very close to having a notebook. We can store things there, but if you want to use it from there, it has to go through this. It would be awesome if we could just vacuum the information somehow, but sadly it doesn't work. How much virtual memory? In theory, we have 64-bit processors. We have 64-bit wide bus. That I don't know how much you know your CPU tech, but we can move 64 bits through a bus. And 64 bits would allow us actually to have 17 exabytes of memory. We're not near there yet. And this is something that we'll need to draw. User mode and kernel mode memory. User mode and kernel mode. I hope those ring a bell. What is user mode? What is kernel mode? User mode, kernel mode, user mode. Mostly Microsoft draws it like this because they talk about memory. But because they draw buckets and things move from bucket to another, people actually get the misconcept that kernel mode and user mode would be locations, which they're not. So before we'll go there, I think it's just important that we understand that on a CPU, at one time, you can only be running one thread. That's executing some function, for example. That's some code that's actually executing on the CPU. Now, this thread has an attribute called the ring, which in Windows can be either 0 or 3. If you ask me what happened to 1 and 2, that's because of US government back in 1989. They decided that the NT operating system has to run on alpha processors, and alpha processors only support 2 rings. So that's why in 2023, we're still stuck with an operating system that can only use half of the CPU capabilities because of US government. I can tell you I had high hopes for Windows 11 because Microsoft said Windows 10 is the last Windows ever. I was so disappointed. Anyway, ring 0 is kernel mode, ring 3 is user mode. Your thread needs 2 things. Your thread needs some CPU instructions because it wants to know how to do something. So like verbs, move things from place to another or whatever. And then it needs access to memory. So it has something to play with. Abilities, resources. When your thread is running in ring 3, which is the user mode, it can only use a very small subset of the CPU instructions, and it only sees its own private memory. If you change that switch, remember the thread is not moving anywhere. There's no place called kernel mode and user mode. The kernel mode and user mode just describe how powerful your thread is. So if you're running with low power, and that's ring 3, then you can only see your own memory and you only have a very few abilities to do anything with it. If you switch that into full throttle, so you switch that into 0, that means that you can access almost all of the CPU instructions and you can see all memory, whether it's yours or not. So no one moves anywhere. Okay. When we're looking at the memory, kernel mode, it's almost like having a single process for everything because it has one virtual memory, and this virtual memory is shared by everyone. If you have drivers running here, code running here, whatever is running here, they all share the same memory. They all use this, which means that if something bad happens here, we have an exception that calls for a function called ke bugcheckx, which actually blue screens the machine. Because we're sharing a memory location, that means that we have a possibility of memory corruption, data corruption, security vulnerabilities. Better to call it quits. Remember, blue screen is your best friend because blue screen is a willing operation by the operating system. It's always better than crashing. Anyway, that's your kernel mode. And then in the user mode, when you want to run some code like Notepad, then you will have to have a process to run it in. So this will be your process. and that has its own virtual memory. If you want to run another app, it gets its own process that has its own virtual memory, and you can't go here. It's not allowed. They're sandboxed against each other. How much memory? That depends. Let's start off with 32-bit operating systems. 32 bits. 32 bits. If you have 32 bits, that equals 4 gigs. You can't address more than 4 gigs of memory with 32 bits. If you want to verify that I'm correct, just take a calculator and change into a programmer mode here. And then you can go and say that the binary value here, if we put in 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1. How many is that? That's 16 bits. You can see decimal value 65,536 or 535 because binary. So let's go more. Let's now we have. Did I miss one? There we go. 4 gigs. Okay, 32 ones. All right. So with 32 bits, Dave Cutler, Mr. Cutler, the only senior technical fellow at Microsoft. I'm now a chief research officer, and I'm not going to fool you. The reason why I'm a chief research officer is because of the greatest mind in security ever, Finnish guy called Mikko Hyppönen. And Mikko's title was chief research officer, and I've always wanted to be a chief research officer. So I told Marcus Murray, Sweden, that I will not join TrueSec unless I'll be a chief research officer, just as a tribute to Mikko. But I used to be a senior technical fellow, and I was a senior technical fellow because the highest rank of technical expertise you can get at Microsoft is a technical fellow, like Jeffrey Snower was before moving to Google, and like Mark Russinovich was before changing to the CTO role. I chose my title as senior technical fellow because that was a way of making people know me. You know that Paula is my best friend and my biggest enemy, because she's the reason why my titles, many times when I introduce myself, it says best male presenter at something. Because if Paula wins, then I have to be best at something, so I'm the best male presenter. But anyway, we have to make a brand, and I wanted people in the US to know me. I was a newbie back in 2013, Tech Ed New Orleans, my first Tech Ed. And I told everyone that I gave them business cards, and I chose my title as senior technical fellow because then everyone would get my card. They would be talking on the corridors like, did you know that Mark Russinovich is only a technical fellow, but there's this young guy from Finland who's already a senior technical fellow. Now, for a long time, many people thought that there are no senior technical fellows at Microsoft, but actually there is, but it's a Highlander thing. So only Dave Cutler is a senior technical fellow, and there can be only one, which means that as long as he's alive, no one's going to be a senior technical fellow. He's the only senior technical fellow at Microsoft Corporation. Now, Dave Cutler built NT. This year will be the 30th anniversary of Windows NT. I hosted a conference for my 40th birthday, and I had Paula speaking, I had Mikko Hyppönen speaking, I had Benjamin Delpy speaking about Mimikatz. It's really cool. Maybe I should actually host an NT 30th birthday party. Windows NT turns 30. That's actually horrible because I'm 43. Oh my God. Okay, anyway. So NT 30 years ago, back in 1993, it was introduced, but they started building it with Dave Cutler and the team coming from Digital Corp. And they started building it in 1989. So 1989, Dave Cutler decided that 32 bits gives him 4 gigs of memory, and he decided that when you have 32 bits, and that 32 bits gives you 4 gigs, he decided that he's going to split it into 2 gigs for user mode processes and 2 gigs for kernel mode processes. Now remember the concept of the CPU rings. That's why he has to have this. This is done by the CPU, not NT really. but he has to split the memory so that what is the memory that is actually accessible only for the kernel mode and what's accessible for the user mode as well. Okay, 2 gigs, 2 gigs. You have to remember 2 gigs was astronomical. So 2 gigs was back in 1989. Silicon graphics, high performance graphics workstations costing tens of thousands of euros nowadays money, today's money. They had a whopping, I was actually acting in a TV series called Cyberwoman. Dark time in my life, but anyway, back in 1994, and we were acting. So you didn't have green screens back then. You had blue screens, not just on Windows, but I mean blue screens on where we now use green screens, and we would act against those blue screens, and everything was drawn with computers. And we had silicon graphics, high performance workstations flown in from UK because Finland didn't have powerful enough computers for drawing those 3D graphics. And those computers had 16 megs of RAM. Think about it. 16 megs of RAM. So having a maximum of 2 gigs of virtual memory was insane. Just astronomical. That will never, ever be a limit. Well, never say never in IT. Things are very different nowadays. Some of you have seen maybe my sessions before. There's, for example, one of my favorite toys is I bought this when I divorced. I bought this lightsaber. This is one of my favorite toys. So it's not a it's not a toy. This is a really, really cool lightsaber. It's from Ultra Sabers. It's like 550 euros, and it's like super cool. Okay, it's combat ready. So it actually has its own operating system and development language. And this one has 128 megs of RAM. So my lightsaber has 128 megs of RAM compared to the high performance silicon graphics computers back then having 16 megs. So nowadays it's small, that's for sure. But back then it was astronomical. There were certain companies with gigantic databases. One example would be MasterCard. MasterCard transfers more money in a night than the European Union has budget for a year. So the transaction amounts are insane, and they use very big databases. Back then they had so big databases that they wouldn't fit in that 2 gigs. So Microsoft came up with what was known as a 3GB switch. So if you use this 3GB switch in your boot.ini file, then this would be changed so that it would actually be this 4 gigs would be split so that 3 gigs went to user mode and 1 gig only for kernel. Now, of course, nowadays we are more talking about 64-bit operating systems, but let's see this. So this means that in a 2 gig world, this would have 2 gigs here, this would have 2 gigs here, and this would have 2 gigs here. In a way, it looks like 6 gigs. But it's only virtual memory. It has absolutely nothing to do with physical RAM, okay? Now, if we change from 32 bits into 64 bits world, 64-bit world, then things are very different. So 64 bits would actually give you 16 exabytes, but this is limited heavily. So we are not near 64 bits yet. So 64 bits depends. If you're running an operating system, which is Windows Server 2012 or Windows 8.0, then you are supporting 44 bits of memory, which equals 16 terabytes, which is split into 8 terabytes for user mode, 8 terabytes for the kernel mode. If you are running something that is Windows Server 2012 R2 or Windows 8.1, then you support 48 bits of memory, which is 256 terabytes, which is split into 128 terabytes for the user mode, 128 terabytes for the kernel mode. So when we go up here, the numbers, you have either 8 terabytes or 128 terabytes, depending on the Windows version. And then on the user mode side, remember, these are still 32-bit processes, so they do not benefit. They will be 2 gigs unless they have a flag set by the developer called large address space aware flag. If that's set, these can go up to 4 gigs, the maximum with 32 bits, but no higher. So when you have a finance department person running huge amounts of plugins, which makes them run Excel 32-bit, even if they want you to buy them a 32 gig Surface Book 3, I mean, that doesn't help Excel. When you have 64-bit Windows and you have 32 gigs of RAM, you can run more Excel side by side, but the single Excel doesn't get a boost until you move into a 64-bit process. So then when you have a 64-bit process, then that process itself will either have 8 terabytes or 128 terabytes. And then it will benefit more. When you are talking about how much memory your computer can commit to giving to applications, we talk about commit charge. So we do have a concept of what's known as page file. So your system can commit to giving certain amounts of memory. It doesn't have to commit to give it from RAM. But one of the most important things that you have to get from today is to remember to make sure that you understand that when you have like RAM and you have, let's say, 8 gigs of RAM, and then you have a page file, which is 4 gigs. This does not mean that you would have 12 gigs of memory. This is absolutely incorrect. Page file is not extra memory. What you will have with this, which is true, is that you will have what's known as a commit limit of 12 gigs. That commit limit is a limit where Windows commits to giving certain amounts of memory for apps. It won't take more than it has this commit limit for, but it does not necessarily have to come from RAM. It could be backed up by some packing store like a page file. Commits to that. That commit limit will increase with a page file, but not memory. So if you think about page file and RAM, you have to remember this. Page file, the traffic goes like this always. So if something's in your page file, it was once in your RAM. If you want to read something from the page file, it needs to fit in your RAM. So if you would have 8 gigs and 4 gigs, that would give you a 12 gig commit limit. But if the application that you're trying to run needs 10 gigs of memory, otherwise it won't work, it won't run. It will not fit in your memory. So it always has to fit in your memory. You can use a page file to store things now so that you have room for other things in your RAM. It's not extra memory. That's what we already went through. One thing that is actually funny here, you can see an example is we have the 32-bit notepad on the left side, then we have a 64-bit notepad running on Windows 8 in the middle, and then you have a 64-bit notepad running on a Windows 8.1. Remember, this is a security feature as well, because if you're hiding things in memory, like you have a bit, malware tries to find an important bit from your memory. It's like finding a needle in a haystack, and this is the size of the haystack. Bigger the haystack, the longer it takes to find the needle. So it's also a security thing as well. It's kind of funny. Server 2003, those of you who are old enough. Server 2003 and Server 2003 R2, Microsoft told us that there's no difference. That's what we were taught. There's no difference. Windows Server 2003 R2 was just Server 2003 Service Pack 1 on another CD, and then some additional features on the other CD. So application compatibility was 100% between those two editions. Since then, R2 has meant the biggest changes in the history of Windows. 2008 to 2008 R2, you moved from a one-part Windows Vista kernel into a two-part Windows 7 kernel, the biggest change in the history of Windows. Next biggest one was from Server 2012 to Server 2012 R2, when we changed from 44-bit addressing to 48-bit addressing. So R2 is nowadays biggest change possible. So this is something that you should understand. If someone was very careful, if you listen to me very clearly, and you might have spotted it, that in a way I kind of like mentioned something that doesn't really make sense, because I said that if you have a 64-bit address space and your application starts from 0 and the maximum is FFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFfffffffffffffffffffffffffffffffffffffffffff because we're not using 64 bits. We're only using 48 bits. But it is still starting from 0 and ending up at FFFFFF. Because the black hole is actually in the middle. So when an application looks at the virtual memory, there's a hole in the middle. So you actually get 24 high bits and 24 low bits. And the in between black hole is shrinking until we get to 64 bits. But if someone's wondering about 128-bit computing, we're not in a rush, at least when it comes to memory. But it is really the black hole is there in the bit in between. You can see it here as well. Oh, sorry. You can see it here as well. If someone was wondering why you could have, like 10 years ago, more than 10 years ago, way more than 10 years ago, should I say 20 years ago, you might have servers that had 32 gigs of RAM. How is that possible that you have 32 gigs of RAM if you have a 32-bit operating system? Well, because it's not extending the virtual memory. So physical address extensions and address windowing extensions, they allowed you to have more RAM, which meant you could have more of those apps running side by side because there was more room for 4 gig memory spaces. But that would not change the virtual memory. So physical address extensions, you might have had a server that supported 32 gigs of RAM, but the virtual memory was still the same. That only allowed you to have more resources to back your virtual memory. Well, I showed you virtual memory already. If you take away the page file, there's still virtual memory. Two different things, very bad user interface. Pages. We have two different sizes for pages. We have small pages and large pages, and this is different depending on the CPU architecture. Most of you are probably working with x64, so that means that you have either 4K or 2 megs. That's a small page is 4 kilo and 2 megs for the large page. when you have these virtual memories on your machine, then the virtual memory is in a certain state. So it could be free, which means it's not allocated for anything. Remember, this is still virtual memory. This is still only virtual memory. So you can think of it like having these pages. I thought I could draw here. Why couldn't I? So, I can. So if you have these pages here in memory, this is your virtual memory. So remember that these pages do not correlate into RAM in that sense. But these could be completely free, so no one's using them for anything. They could be reserved. So someone might have said that I'm actually going to take these are for me. Now my pen stopped working. It does this. This is the new Lenovo Yoga X1, which has this super annoying thing. Well, actually the previous one has it as well. So it's not about battery. It's still fine with the battery of the pen, but it just has to go visit the home nest and then it starts working again. So we could make a reservation saying this is something we are going to use. That's for us, but which actually not being backed by any RAM. So if this is your RAM, this means that we reserved it, but it's not using RAM. Then we have committed, and now this committed means that it's allocated and it could be allocated from RAM. So we could make an allocation here that will be there. If you don't want to use RAM, we could also have it paged into the page file. So committed doesn't mean that it actually is backed up by physical RAM. Some of these pages are shareable because if it's, for example, binary, then this binary here, for example, if this is binary, it could be used by multiple different processes. It's shareable. If it's data, it's not shareable. Only committed or mapped pages can be accessed, so read or written to. And when we have something in memory, we can read it very blazing fast. But if it's not there, we will have to get it from the disk, for example, and then that will cause a page fault. So Windows doesn't read things from the disk. Windows pages things in from the disk. And I can show you that in action in just a second, okay? Your pages also have a access control. So every page which is in your memory, that page it can be marked as readable, writable, executable, and nowadays also no execute. So we have its own access control. It's different than your NTFS or whatever access control on your operating system. The CPU has an access mask for every memory. So the memory controller has a access mask for every one of these. It keeps these information in the page tables. So that page table is what translates memory. Remember, nowadays you might be in a situation where you have to do this memory translation a few different times, because when you really look at it, let me just go here. If you think about it, if this is your app and your app sees memory, so your app sees this memory here, there are a few pages here, then we have to some people will call it flat. So first level address translation. We will translate that into RAM. Okay. So when RAM has a page here, we will just map this here. We will have this mapping here, and it can also have an access mask. So we can say that this is only readable. But now, in all honesty, most of the time, this is actually not RAM. That's virtual RAM, because that's your virtual machines, what it believes is real RAM, but it's not. So we do what's known as SLAT. We've seen that acronym probably many times when you buy new computers. So SLAT is second level address translation, because we actually have to translate this again into what is known as real RAM. Okay, they actually have a this is called guest memory, and this is called system memory. But anyway, so this will be the real RAM, where we have to do that translation one time more. So we actually have to potentially do this many times. Actually, even more. If you use nested virtualization, you would do that again and again and again. When you start learning about cool security features on this training, like credential guard, virtual TPM, stuff like that, they will all rely on this technology because Windows can't keep secrets. So what it actually uses is these second level address translation tables to make things unreadable by the kernel. But you can go YouTube Sami Laiho secure kernel if you want to see stuff about that. I've done it before. When we have threads running on a CPU, they also have to have some places where they can take notes. So they have these stacks. We have one stack for accounting purposes, both in user mode and kernel mode, depending on where it's accessed from. But if anyone's done any development on like basic level languages like C, C++, for example, then everything here makes sense. Because if you're in a process, you can create what are known as global variables. That will be stored in the process's memory because it can be referenced by a lot of functions. If you create a local variable, which is not usable outside of that code, then that will go into the thread's memory. Every processor has some of its own memory. I'm not going to read through all of this. Like I said, some of them you will just, you can go and read yourself. Memory mapped files, very, very important topic. Okay. When you think about the, let's say you have app.exe, this is still in your hard disk. Okay, we're still in your hard disk. So this here is your SSD or your real hard disk, but let's say SSD. Now this application here, this is what mostly is referred to as an image because it's an image of your code. It's your original source code translated into machine language, heavily optimized and compressed and all that stuff, but it's still an image of your code. Okay, so this still has the functions. They're not readable like this, but I mean that's your code. When you need to move that into memory, you need a bucket, and that bucket is what is known as a process. So this is your process. It inherits the name, so it's called app.exe, like you see it in Task Manager, for example, but it has actually nothing to do with that app.exe. I mean, they're both called app.exe, but the other one is an image and the other one is a process. So this app.exe then starts and it takes and it maps this into memory. This executable, all the code that you have, it will actually map that into memory. Now the application believes, the virtual memory shows that all that code that you're using is now in your virtual memory. But if you start reading it, oh, this is interesting. Only through this will it actually move into RAM. Okay, only that part is in RAM now. So only when you need it, it's just mapped into memory. It's just said that it starts from this address, enter this address. It's mapped there, but it's not consuming RAM until you touch it. Then you're gonna have a very, very, very big amount of DLLs. Okay, DLLs are shared code, and these DLLs are then mapped into your process's memory. So this DLL is mapped there. This DLL is mapped there. That's why you can't say like, okay, I want to run Notepad, and someone asks, how much does Notepad need memory? Well, you can't go like this. Notepad takes 400 kilos of memory. Because when you load Notepad like this, and you take Process Explorer, and from Process Explorer, if we look at Notepad now, it's there. Where did it hide? There we go. If we look at Notepad from here, and you change this lower pane view into DLLs, all of these DLLs need to be loaded into Notepad's memory. This means that another sysinternals tool, VMmap, if you look at Notepad from here, you can see that the Notepad loads the image. So it loads all the DLLs and everything into the virtual memory. And if you look at this, you can say that the image, actually this is taking 267K, 267,400 kilos, okay? A lot more than just the small part that we saw as a 300 kilo bit binary, okay? You need a lot more memory because every DLL needs to fit there. Well, the good thing is that DLLs are shared code, which means that DLLs are then shared by all the other applications. So you don't have to, when you have these many notepads running side by side, you don't actually consume that much of RAM because these share most of the code with each other. Because we can map into the same DLLs in RAM. Every process thinks it's their own. But we don't really need physical memory to back it up. docx, great example. So docx, XLSX, Office files, they're also memory mapped files. And just open it in virtual memory. You open a Word document, you say, starts from here, ends here. And when you start reading the pages, it needs to be in RAM. I spoke about process heaps, not gonna drill into that anymore. Those are stored for the kernel in two different pools. We have pools, one is called paged pool and the other one is called non-paged pool. So kernel process memory. I mean, normally application sees the process memory, that's fine. But if we think about the lower part, the kernel part, where you saw that memory that's used by the kernel, that is stored in two different pools. Paged pool and non-paged pool. Paged pool means that we can put it in the page file if we need that memory for something else, and the non-paged pool is something that has to stay in RAM, whatever it happens. We haven't, I don't know how much you've done your Windows internals, but the CPU works different. CPU masks out different IRQ levels, and if you go above IRQ2 mask level, then you can't read anything from the disk anymore. So when your computer is in different states, only the non-paged pool is something that can be accessed whenever, because it doesn't have to create a page fault to get something from the disk. So actually, I don't know if I should have said anything about that, because that might just confuse you more. But let's put it this way. Kernel splits its memory into two pools. Non-paged pool, which can be accessed whenever without making a page fault. And then it has a paged pool, which can be paged into disk if we need it for something else. But there are cases when you can't access that because that would cause a page fault, and we have no one to answer that exception. You don't have to worry about the sizes anymore. When you read something from the memory and it does not exist there, this is very important for performance troubleshooting. Remember that Microsoft still today has a document that says you should never have more than 5 page faults per second steadily. That's bullshit. It's wrong measurement. Even if it says so in the knowledge base article, it's wrong, because page faults in Windows Performance Monitor, Perfmon, they contain both hard page faults and soft page faults. They're very different thing, and only the other one is a bottleneck. When you have a process here, process 1, it has its own virtual memory. Some of the virtual memory is currently in RAM. I mean, currently backed up by RAM. Some of it is backed up maybe by the page file, and some of it is backed by memory mapped files. This part here is what is known as a working set. You see that referenced in many tools, working set. Working set is a process's memory that is currently residing in RAM. Now, when we have another process here next to this, and this process has its own virtual memory. Now, when this one looks for a page that does not exist, it causes a page fault. Sounds horrible, but it's not. It's the mechanism for reading files from disk, for example. When you go to the CPU level, the page fault is actually an access violation. Sounds even worse, but it's not a bad thing. But when we want to look for a certain page, if we can find that page from someone else's working set, that's not a problem. This is considered a soft page fault. If we have to load this from the hard disk or SSD, that is a bottleneck, and it's known as a hard page fault. Those you shouldn't have more than 5 per second steadily. You can measure them very well with Resmon, not Perfmon, but Resmon. Resource monitor, go for memory, and you can see these hard faults here. There's less than 5 steadily. All good. Okay. What if I read a big document? Think about this. What if this here is your Adobe? And you want to read a PDF. The PDF is here. Let's see what happens. Where is Sami? Teaching materials, WinFu, advanced troubleshooting. Let's open Windows internals book number 1. Okay. 294. But it's not steadily, but it's a normal function. It's now reading something, it's mapped into memory, it tries to read it, it's not in memory, it causes a hard page fault, which is then returned from the disk to the RAM, shown on your screen. It'll go out. We're also needing MSMBeng, which is the Defender engine, because we need to scan it. We are using MS-Sense because I'm very heavily protected by TrueSec with my own TrueSec computer. So Sense is there. This is the Windows Defender for Endpoint engine talking to our SOC and all that stuff. So it's going to go down. It's not a problem if it's there for a short period of time, but it should go down. So page fault might sound like very negative, but it might not be very negative. So soft page faults are normal. You have a Citrix server, you have soft page faults like 500 per second all the time. And it's completely fine because it's half the speed of light. I hate SAP consultants. I'm sorry. If any of you are an SAP consultant, I'm truly sorry. I hate them. Why? Because they make more money than I do. So they just have bigger hourly payment than I, which is not very easy in this country, but they do. And the other one is they have absolutely no idea how operating systems work. So when I go to a SAP consultant and I tell them that I have a problem, SAP is slow queries. Answer is always, yes, we have a solution for you, buy 64 gigs more of RAM. They don't know anything else to say, but buy more RAM. If you're looking at the memory here, well, if this bar here, if it honestly goes green, like here, if this is all green, then I'm quite sure that you should buy more memory. Yes, common sense. If you're almost all out of memory, so you should probably buy more. Now, what you should look when you have any kind of memory issue and you're thinking of buying more memory, one thing you should always look at is this hard faults here. So, oops, sorry. Let's try that again, like that. And so if you see values here like 120, 12, 12, 12, 12, 12, 12, 12, 12, 12, 12, whatever. Yes, you probably should buy more memory. Because honestly, many processes in your computer are suffering from not having that data resident in RAM, and they need to rely on the disk. Yes, buy more memory. But if you look at this and you see this, okay, I'm just joking, but whatever you see here, you see some sort of an application and it says 234 hard faults, and no one else is suffering from running out of RAM. It's just a crappy application. There's no benefit in buying more memory if you have a piece of beep application. We talked about commit limit. You can see your commit limit on this machine here, for example. If we go for, sorry, I need task manager for this. It's different looking in different versions, but if you go here for memory, for example, here you can see your commit limit. The first value is commit charge. That's how much you're currently using out of your commit limit, and that's the maximum. And the maximum is your RAM plus the size of all of your page files, and this can increase automatically. So Windows will increase the size of the page files. Windows will create even new page files if needed. I spoke about working set. I'll show you these working sets a bit later on. Before we hit physical memory, let's look a little bit at how this virtual memory and physical memory behave. So what I'm going to do is I'll take a virtual machine from here. Add a debugger. So what we can see is we have let's increase that a little bit, and let's open Resmon at the same time so we can see the memory footprint of this machine. I got quite a lot of free memory here. And whenever you're looking at memory, remember, do not ever look at this. Just stop looking at this. You should look at this. You should have enough available memory, but you should never have free memory. This is unused resources. It's like me, my family runs a clothing factory. Wouldn't it be awesome if you had you had these employees standing here in line, and if someone gets sick, you just get an employee from there to replace the sick person. It's freaking expensive, at least in Finland with the salaries that we have to pay people. You honestly, unused resources if you have people standing there in line, not doing anything. Well, let's just try this out a little bit. So I'm going to use a tool called test limit. You can use it as well. Test limit is a really cool sysinternal. Oh, sorry. Well, it actually just worked, but I assumed I would get an error because I typoed the wrong language keyboard. So test limit, and this is your best tool if you want to learn about how memory works, because you can create memory reservations instantly. So you can, for example, let's do test limit, and we will do M or D, leak and touch memory. Let's do M, leak memory, okay? So what I'll do is I'll just leak memory 1 gig, the counter of 1, okay? If you go here, you can find test limit from here. Now test limit here, if you look at the values that we have, then this did that die already? Why did it go red already? Died. No, it did not. Where is it? Oh, it is there. Sorry. Just when you check it, then it should stay on the top. There we go. Now we have it. Okay. So you can see that the commit is like 1 gig, but it takes 5 megs of memory. So actually like working sets. So the virtual memory reservation is huge, but it doesn't really need memory. And you can see that if I do this, you can take a look, you can keep an eye on the green bar there. So if I kill this, and now let's do that 2 times. You saw nothing happened. That's just virtual memory. If I do the same thing, but I'll change this to D so that we'll actually use it as well. You can see that now we're actually using memory, okay? Because we touched every page. And this is honestly the easiest way to really learn how the memory works. You can also very easily see the difference between a 32 and a 64-bit. So if I'll say test limit dash M, just let it leak, and it can leak 4 gigs of memory, not more, because we run out of virtual memory. But it actually ran out of memory so badly that I can't press Ctrl+C anymore, because Ctrl+C in that process requires a memory allocation, and I can't allocate memory anymore, so I have to get another command prompt. Test limit 64. It leaked 22 gigs of private memory, and then it has to start to increase my page file because I ran out of commit limit. Okay, I'm gonna just kill it. Okay, I don't want to actually be using any more memory. Windows will do whatever it takes to try not to actually die from a out of memory condition. If you want to test that out, then I will recommend Not My Fault from sysinternals. And with this one, what you can do is you can start to leak memory. And what we can do in the background is you can see the used memory, and then we can see the working set sizes here. And what Windows does is first it eats away all the free memory because that's not used for anything. Then this blue one is cache. So that's your cache, which just keeps things in memory if you might use them again soon. So this caching here, it will eat out that cache. Then it will start asking for the other processes to give their memory to you. And then at some point it will actually die when it runs out of memory. It's hard to believe, but back in 1995, the most sold software in the world was Windows 95 upgrade. That's not hard to believe. That's actually easy to believe. But the second most sold software was a memory optimizer. And that memory optimizer would free memory in Windows. Second most sold software in the world. Mark Rusinovich proved that it was not doing anything except making your performance degrade, but it didn't do anything. Company went bankrupt. Mark became famous. I'll show you a memory optimizer. Okay, so what it did was exactly what I'm doing now. I'm just going to tell this that leak memory. Please leak memory 50 megs at a time. And I'm going to say that it has to be leaked so that it can't be paged into the page file. So what we'll see here is now we're starting to eat the memory. See, I had 5 gigs of free memory. Okay. And you can see all the free is first eaten out. So this is what the second most sold software in the world in 1995 did. Filled the whole memory with garbage. And then when it had filled it with garbage, getting all the RAM at it that could from everything you were trying to run, making everything slower than ever before, it would just kill itself. Oh, huge amount of more free memory. Yay! Don't look at free memory. Okay. Physical memory stays in different lists as well. So the physical RAM pages are kept in different lists. We have free page list, which is completely unused, the light blue one. We have modified page list where we have something on a page that we could use for something else, but it still has content in it, which is not backed up by the disk. So we can't yet give it something else. Then we have standby page list where we have pages that can be used for something else, but because it still has the content, it's used as cache before we need it for something else. And then we have a zero page list where we have to put things that, well, if you have content in the physical memory page, it has to be cleaned out. Virtual memory can just disappear, but physical memory, if that memory page has content in it, and if it's data, then it needs to be zeroed out first. There's one thread in Windows called the zero page thread, which only job is to write plain zeros into memory pages. Few memory protection techniques that were introduced in Windows XP. The first one, XP Service Pack 2, and the second one in Vista. So data execution prevention, make sure that if you have some data stored in a memory location, we can make sure with a no execute access mask that it cannot be executed. This was built for these buffer overflow faults. Early days when you put more than 256 characters to the address bar of IE, everything after that would be executed as code. And this was built specifically to mitigate those. ASLR, even in Windows 10, even in Windows 11 Enterprise, there is one bit in the kernel that says whether the password is correct or not. If you can find the bit, change it to 0, you can use any password you want to log on to Windows. But you can't find it because in Windows XP, it was still in a predetermined location. So you knew where to go and switch it. It took 2 seconds. But since Vista, The address space layout randomization makes it so that it will be in a random location, which means that you have to search for it first. Now, the bigger the haystack, the longer it takes to find the needle. Few tools, if you want to see whether your application, which is not running currently, if it's running currently, you can use Process Explorer, even Task Manager to some extent to see if it's 32 or 64-bit. If it's still in the disk, you can use SIGCheck from sysinternals. It shows you whether it's 64 or 32-bit. If you want to know whether your application can handle more than 2 gigs, if it's 32-bit, you can use the you can use dump bin tool from the SDK. If you're interested in how your physical RAM looks like, I mean, you're really interested in what is in a certain physical memory page in my RAM currently, or what is my RAM being used for currently. RAM map, okay? RAM map is the physical layout tool. It's really interesting. I mean, I really like it. So if you run RAM map, it takes a while depending on how much you have memory. And it shows you what your memory is used for. This is as true as it gets. Shows you those that we talked about, the different memory states or memory pools there are. And then it shows what it's used for here. So this is kind of a summary. And then you can go for file details, or actually probably file summaries better. And you can go and check, for example, how much memory is consumed by what. And MS Edge DLL seems to be taking a lot of memory. Usually Teams is here, but what is usually actually here? I mean, if I look at these, then usually what takes the most is actually not the Edge, it's actually my Outlook's OST file. My Outlook's OST file is really big, so that's usually on the top. It's very, very interesting. If you're interested in what the application sees the world like, then it's VM map, which I showed you earlier. VM map is very good for figuring out memory leaks as well. So what you can do is you can use VM map. I had it here already. Normally, the timeline down here is grayed out. So you can either press F5, or what you can do is you can just instrument the application from here. So choose select process and say that you want to launch and trace it from here. Now, if we say we want to see Notepad, and we'll just whoa, what did that do? There we go. So here we have Notepad running. Now you can see that the timeline is active here. And if I go here and I'll just consume some memory. So I'll open up something that we have, like we need memory for something. So let's use an open dialog here. That requires memory. Like that. Now, if we go back here, what you can see is you can go to timeline and you can see actually a huge increase in the memory usage here. What you can even do is you can pause this and you can use your mouse and you can say, I want to compare this time to this time. And it will show you increases and decreases in memory and also what it loaded more or what it gave up. So memory analysis, depending if it's virtual memory, VM map, if it's physical memory, RAM map. If you're using the debugger, BAM VM. If you're interested in what in your computer is actually consuming your memory, device manager. Device manager, and let's change the view and say you want to see resources by type. And then you can go memory and you can actually see what needs your RAM. What is consuming your RAM? when it comes to your devices. Sadly, no numbers, but hex. But still. Now for the interesting thing, myth busting. Okay. What are backing stores? What are page files? When I started my career, I think that if you think about how many different ways of managing, how many different ways of tweaking the page file, I think there were as many ways as there were instructors. Everyone had a different opinion on how you would size your page file, where to put it, if it's static, blah, 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 blah. Let's do some myth busting, okay? So this is super fun. I really like this part. Biggest mistake, do not take away your page file. It's not stopping paging. That is the very common myth on the internet. Many people say it like that. You take away the page file so Windows won't page the disk. It'll usually page even more. People don't understand. Don't read those instructions on the internet that say how to tweak the performance of Windows 10. Usually just don't. Microsoft was actually asked because Ars Technica got into so much trouble by having this really bad instructions that would start people's computers with blue screen. And they asked Microsoft, can you ask someone from the kernel team, some senior engineer, to just write us an article, how to tweak the performance of Windows 7, so that we would have an official opinion. Microsoft said yes. This guy called Jamie, he wrote the article, and I can tell you because I know it by heart. The article goes like this: please install Windows and keep using it, Jamie. If you want to, if you really want to have a Windows 10, I'm a Microsoft MVP for the core operating system. If someone, I really know how to tweak the operating system, but I also understand not to tweak it, which means that if you want to have a Windows 10, which is actually the most secure Windows 10 ever with no known viruses, there is a Windows 10 you can buy, which is completely tweaked for the best possible page file settings and the best possible performance you can get from a Windows 10 machine. You get it from the store. It's called Xbox Series X. I just got this. I just got this from my kids for Christmas. So it's actually a where does it open? It's a fridge. It's my Xbox fridge. Looks like a Series X, but I have a Series X there as well. This is way bigger because it's my fridge. But anyway, that's your tweaked Windows 10. Stop tweaking. You have one, buy it. It's a game console. Okay. Now let's talk about page files. So first of all, take Notepad. What gets paged into a page file? I have Notepad here. I have this text here, like that. Okay. From this Notepad, what goes into the page file? This is my Notepad. I have the executable. I have a gazillion DLLs. Okay. See, I mean, 70, 80 different DLLs here. Huge amounts of DLLs here. And then I have some data. That data in this context is the text you just saw on the screen. Page file is one of maybe 1,000 backing stores on your disk. So when your disk here, when it has the page file and you're running out of memory, the only thing that goes into that page file is this text. All of these use the file itself as the backing store, because they don't change. They don't have to go to a page file because they don't change. If you need to give that memory to someone else, it doesn't matter because we can just page it back to the file itself. So the backing store for that binary is the binary file itself on the disk, not the page file. So in this case, that's very small few bytes of memory actually goes into the page file. If you go and remove the page file, that doesn't stop paging. That just stops the processes from paging their private bytes into the disk. Only way to stop Windows from writing to the disk is running WinPE. Should you tweak the page file settings? Absolutely not. 99% of cases, you leave them exactly like they are. There are the most retweeted tweet from Ignite 2016. 2016. Well, yeah, Ignite 2016 in Atlanta. The most retweeted picture of the whole conference was a picture of my slide, and that slide said, "It currently takes 100 engineers at Microsoft to understand everything about Windows. Please give yourself some slack." They have the 100 most talented engineers working with these settings, yet you result in reading blogs about how to tweak Windows performance. I have a Finnish company that has 10,000 consultants, 10,000 workstations. They can't create memory dumps. They can't analyze any kind of bad bug checks, bad blue screens. They can't analyze anything because their boss changed the image so that they changed the page file from the C drive to the D drive because he thought it's faster, because he read an article online called "How to Tweak the Performance of Windows 10. I confronted him. I asked him, "Why did you do this?" He showed me the article. I found this online. It was really cool because I backtraced it to the author, and the author was an 11-year-old kid. So in Finland, 10,000 enterprise computers can't analyze memory dumps because of an 11-year-old kid written blog. Pisses me off. That 1% that might tweak these, first of all, they have to be single-purpose machines, like a game console. You don't use them for office and playing games. You use them for a single thing. If you use them for multiple things, tweaking starts to be really difficult. You should not do that. So if it's a certain server where the product group says page files need to be set like this, maybe they know better. But that's, again, a single-purpose machine. Computer experts. I mean, you really know what you're doing. There are people who don't want to use a page file, but they have 7 laptops that they can use, so they couldn't care less about trying to analyze some faults. They just throw them in the garbage if they want to. If you have a very small C drive, or let's say you have a 100 gig C drive, but you have 2 terabytes of RAM, you probably don't want to have a very big page file on your C drive, at least not being big enough for a memory dump. So people forget that page files are the place where the blue screen writes the memory dump to. So when your computer crashes to a blue screen, there is a function called KE bugcheck X, which masks the CPU so that your Windows can't do anything. And then it takes the content of your memory and dumps it into your page file.sys. When the computer reboots, it opens the page file normally, finds a header in the page file, and figures it's a memory dump, renames it to memory.dmp, and creates a new page file. When we have a blue screen, we can't ask for favors. We can ask for favors from file systems, so we have to use a file that has a handle open to it, and we know where it is, so we use the page file. Or a dedicated dump file, if that's set by a registry key. You should also, of course, figure out if you're really using it. So you can use Resmon. It can actually show you if page file is used. You can use Procmon, but remember that Process Monitor, the default filter filters out page file. So you have to take it away from the default filter if you want to see if it uses the page file. If you still want to optimize after everything I said, just add more RAM. It's not that expensive. If you can, just add more RAM. If you still want to optimize, I think nowadays probably the best call is to get a small SSD, doesn't cost you anything. Get a 32 gig SSD, doesn't cost you almost anything, and it's perfect for a page file because it's blazing fast. Remember, if you move the page file away from the C drive, you cannot create a memory dump. What you can do is, if you have C, then just don't remove it from the C and move it to the D. Okay, so don't just do it that way, but leave it in both 2000 and 2000, because Windows does a latency check against every page file, and it uses the fastest one. So you don't have to worry that it would use the C drive, because people remove it from the C because they think that it's used somehow. It's not. So this will be used first, but now you can still create a memory dump if you're just looking for performance. If you don't have room for this in the C drive, then I get it. Page file placement, just said, static page file. Myth busting number 2. When your computer crashes, user mode, kernel mode, something goes south in the kernel mode memory, there is an exception here. The exception handler for this is a function called bugcheckx. This bugcheckx starts to dump the content of your memory into the page file. Now, if you set your page file to static, which was a recommendation 10 years ago by almost everyone, it didn't really make any sense, because what you would say is that you would put it as static so that it wouldn't fragment, because you had spinning disks. So you would have a non-fragmented page file. But the first time your computer crashed, that content of memory would be written into that page file, which would be then renamed into memory.dmp, which meant you would have a non-fragmented memory dump. And then it would write a new page file all over the disk. So it was really only good as long as you never crashed. But then 10 years ago, we had a lot more crashes than we have today. No page file at all. Usually it's a net loss. Usually you page more to the disk compared to having a page file. You can only explain this with a good picture. Thanks for guys from ACUS for lending me a picture. So left-hand side, this is a really, really good slide. So, and it's not done by me, so I can just brag about it. It's not mine, but it's really good. So the left-hand side, you can see that there is a page file. So there's a page file here. And on the other side, there is no page file there. Okay. This is the virtual address space in the middle. Now, because we can put more stuff of our private memory into the page file, this means that we consume less RAM for that content, which means we have more room in RAM for all of the gigantic big memory mapped files, which means that we don't have to go that much to the disk to read these. If you remove the page file, you're going to use a lot more of your RAM for that private memory, which means you have less space for all those gigantic big memory mapped files, which means you will page more to disk. the magic here is to understand that page file is one of maybe 1,000 different backing stores on your Windows. Only for the private memory of the processes. Sizing of the page file needs to be, just don't touch it, it's the best one, but if you start sizing it, it needs to be big enough to house the memory dump that you're going for. Kernel memory dump, usually talking about some hundreds of megs up to a gig, but totally depends on the case. I can't say any, there's no sure way. The only thing I can say that on a 64-bit machine, it will never be more than your RAM. On a 32-bit machine, 32-bit operating system, it's maximum 2 gigs. But for a full memory dump, maximum that you would never ever need would be size of your RAM plus 256 megs for driver dumps plus 1 meg for header information. That would be the absolutely maximum you would ever need. Depends on what your setting is for the memory dump. I was a senior technical fellow when Mark Russinovich was still a technical fellow, yet for some weird reason, it seems that people will believe Mark Russinovich more than Mr. Sami Laiho. So just in case, Mark says slide. This Mark says slide is a quotation from Mark about sizing the page file. To optimally size your paging file, you should start all the applications you run at the same time, load typical data sets, and then note the commit charge peak or look at this value after a period of time where you know the maximum load was attained. Set the paging file minimum to be that value minus the amount of RAM in your system. If this value is negative, pick a minimum size to permit the kind of crash dump you're configured for. If you want to have some breathing room for potentially large commit demands, set the maximum to double that number. Not sure if it's exactly the same that I told you, but close enough. Last thing, Windows 10 changes this. So what happens with Windows 10 is that in a normal case where if we need memory for something else, we can trim it out of the working set. So in the working set, I'm not drawing again. This is very annoying. This happened too many times today. Everything has a firmware, so maybe this one has a firmware upgrade as well. But now we have this here. So you have the working set here. We can trim those. It's called trimming. We can trim those memory pages and we can move those memory pages to the modified list. That's where they have to be as long as they have something that's not backed up by a backing store. Then when the content is written from there into the page file, then we can move that page into the standby list because it's backed up by page file, but it's not cleared yet. So it works as cache. And then if we need it for something else, we can move it to the free list, or maybe we have to put it to the 0 list. This is what Windows did up to Windows 10. Remember, when you have pages on a table, you can read these pages. But if this table is your memory, now even if you have a page file, you have to remember that if you want to fit a new page to that table, you can move something to the page file so that you can get something else onto the table. So you can move something out so that you have more room for something else. But remember, page file is not extra memory. It's just a backing store for your memory. But now that we think about it, if these are A4s on a table, then there is one way of keeping all these papers on the table, but have room for more papers. And that is to wrap them into balls. Okay? We can have more of them on the table, but now there's an overhead because if you want to read the content, you have to unwrap it first. So this is how Windows 10 changes this process. what happens is that when we start trimming something, instead of writing it to the page file, we actually do whatever it takes not to write to the page file. But what we do is that we actually, instead of that, when you have the data here, still the data on the page, what we do is we put it here, but we compress it so that half of that is freed, and we can take half of it and we can just trim it out. We can just put that free here. If we really run out of this memory here as well, we can actually start pushing that into the page file, but there's less IO here because we are putting compressed data in, less IO operations. So Windows 10 does whatever it takes to not write to the page file. First, it tries to compress that stuff and keep it still in RAM. Because it doesn't cost that much to decompress, because modern CPUs are blazing fast. They can decompress memory content 7 gigs per second. One page is 4K, so a lot. And on the other hand, it's faster, so it's keeping your computer faster. But there's one thing people do not remember. One important reason why you have this. SSDs. This here, this is an SSD. The less you write to an SSD, the less it wears out, the longer it lives. So you should do whatever it takes to not write to the disk, because our SSD lives longer as long as we can keep things in RAM. So that's a change there. All right, there's a few slides. As I said, not going to go through everything. I do not know how you felt like, but I feel like the clock should only be 9. I mean here, because I think we just used an hour, but it really looks like we used 2 hours.